Well, hi again, everybody, and welcome to Dodger State. No, not that. We are in math, and we're in section 3.8. This particular section deals with population growth, radioactive decay, Newton's law of cooling and heating. I'm going to try to hit all those problems, and that'll finish section 8. But basically, exponential models are very common in STEM. They are very useful. They're fun to play around with. There you have it. So we're finally going to see our math being used. So down here, growth and decay, I have a lot of notes for it. They're for you to stare at and whatnot. The first time we've heard this, we're in Calc 1, but I'm staying a term that you kind of see more and more in Calc 2. It's called a differential equation. Basically, what they say in the textbook is the rate at which a population increases or decreases. Basically, it changes directly proportional to the current quantity. So that is, the more mice you have in the field, the more mice per year are growing. A small population yields a small rate, 32 mice per year. A large population, large rate, 3,200 mice per year. So it's proportional. Here's how you write it in math. It says basically the rate at which y is changing is directly proportional to the current y value. Okay, so what happens is, I say you can easily verify that this function is a solution. What you do is you take its derivative, you plug it in on the left, you notice that it's the same on the right. And you can easily do that. I'm not going to do it, I'll let you do it, but you, again, derive y, find dy dt, put it in on the left, compare it to k times y, which is this y. All right, population growth, radioactive decay. These are the two guys that we're dealing with. Typically, and these formulas are what we use for these types of problems. I have a couple of examples to show you. One you do, one that I do, etc. Okay, so basically, these are notes for you to help solve the thing. Typically, you're given two data points. You use one to find the initial population, the start of the experiment, so to speak, how many mice were there at the beginning, and then use the other data point to find the all-important growth constant k. Once you find these, you can answer all kinds of questions. And with population, oftentimes they talk about doubling time. The radioactive decay is similar, except it's falling, not rising, decreasing, not increasing. And in that case, not a doubling time, but what they call a half-life. A half-life is actually a measure of time, just like a doubling time is a measure of time. And it says it right there what it takes. Newton's law of cooling says basically you take an object, you put it in a warmer environment, or it could be a cooler environment, and you're going to watch the temperature of the object change and either increase exponentially to the surrounding temperature or decrease exponentially. And in this case, he's saying Newton found, or you can kind of surmise, hey, look, the hotter an object is in a cooler room, at first its temperature is going to change quickly to accommodate, but as it gets closer to the surrounding temperature, the changes in the object's temperature are smaller and smaller. So you have this kind of picture or image where you have, like, this is the temperature of something and this is time, and you got the surrounding temperature happening here, whatever it is, I'll call it T sub s. And either, oh goodness, where'd my little guy go for the colors? Well, I don't have the colors right now, I don't know why. I'll just keep going. Either you're dropping down towards the temperature or you're rising towards the temperature. So let's see this stuff in action. It's really cool. I'll show you how to do these guys. And it's the same method every time. Sorry, let's do one of these guys. Here we go. Example. A certain type of bacteria given a favorable growth medium doubles in population every 6.5 hours. Given that there are approximately 100 bacteria to start with, how many bacteria will there be in a day and a half? Now, one thing I didn't notice when I used my calculator, I got ready for you guys, I didn't notice the day and a half as opposed to hours, and that's going to be a thing, right? Anyway, so basically what you do right away, it's a population, so you can write down population is P0 e to the kt, right? All right. Still recording, right? Okay, cool. P0, what's P0? That's the initial population. And P is a variable, population. T is a variable, time. E, you know E, and K is the growth constant. So every time I do a problem, it's kind of cool to lecture it this way. There's T, there's P. When you plug in 0, you get the initial population. What did they say it was? Oh, I didn't read it. Yeah, I did. 100. So there's 100 bacteria at the start, and it said it doubles every 6.5 hours. So in the time column, if I go up to 6.5, it should double to 200. Okay, so the first one is going to tell you your initial quantity. It always, if you plug in a 0 for T right here, okay, e to the 0 is 1, and so the population should be this coefficient, the initial population. So right away, since you're given the initial population, the function becomes P equals 100 initial bacteria times e to the kt. All right, now we use the second data point to find K. Apparently, if you plug in 6.5 for T, you get 200. So I'm going to plunk a 200 here. And maybe you remember doing some of these yourself, but here I've got 6.5. And now to find K, it's a matter of just solving for K. It's an exponential equation. Well, divide the 100 over. Okay, so we've got 2 is equal to e to the 6.5 times K. Next step, natural log 6.5K, and you know what? Here's a computation for K. K is equal to the natural log of 2 all over 6.5. Now that one I plunked into the calculator if I can find it. It is about 0.1066. So the number itself, I think that's right, it's interesting, but it's not important. What I do is I store in stow, as in, let me get better at that. There's a button on the calculator, STO. I store it in the calculator. Okay, that's what I do. Now I know what K is. Now I can answer the question. The question is, how many bacteria will be there in a day and a half? Here's where I blew it. 1.5 days is the same thing as, well, 24 and half 24 is 36 hours. If you're working in hours, you're working in hours. So you go to your table up here and you go, how long does it take? What is it again? Oh, how many bacteria in actually, I can't put 1.5 here because right now I'm thinking, and I should have written this, I'm thinking hours. And all the others, you should do that too. So here is 36, and the question is how many bacteria? Well, you use this is where you get to use your formula, and your formula says, hey, P, when you go 36 hours out there, right, is equal to what? 100 e to the k times 36. And you use the stored value and you use your calculator. I got about 4648. So 4,648 bacteria is the answer. Ta-da! Math in action. Okay, that's how that's done. Now you get to pause it. Do this next problem right there. So pause it and do it. That was 1, 2, 3. Okay, now you play it again and we're going to do this one. This time it's a half-life problem. It says, how much of a radioactive kind of cadmium will be left after 42 years if the half-life is 14 years and you start with 80 grams? Well, I'll use different letters, but don't you know, it's the same function, isn't it? Just different letters. I'll use this one. Why not? Okay, what does this mean? I think it really helps to see a table. How much? You start with 80. See that? You start with 80 grams. When you start, T is 0, you've got 80. So there's your initial quantity. So I'm going to put an 80 there, e to the kt. But then they said the half-life. Half-life, 14 years, you have half of what you started with. Not doubling, halving. That's what half-life is about. So we use this information and we go, apparently we get 40 when we plug in e to the k times 14 years. So you're supposed to divide, You're going to get a 1/2 here is e to the 14k. That means that 14k is the natural log of 0.5. And therefore, when you divide by 14, you get a k value. And for that one, I can't find you. There you are. About negative 0.0495. It's about negative 0.0495. 0495. That's just a number. That's just a number. Notice, though, this is the thing. Up here where you're growing, k is positive, isn't it? That means growth. Down here where you got a negative, that means decay. And the model's taking care of it for you. Okay, so the last question is how much is left after 42 years? You just go Q is 80 e to the k times 42. You do the computation straight up with a calculator for that one. I got exactly, it's weird, I got 10 grams. I hope you did too. One of us has got to be right, right? Okay. Now I think, yeah, it's Newton's law of cooling. This one's crazy. Okay, so there's a little bit of thinking at the front end, but the problems are done the same way. Okay, so let's read it. A cheesecake is taken out of the oven with an ideal internal temperature of 165 and is placed into a 35-degree refrigerator. After 10 minutes, the cheesecake is cooled to 150. If we must wait, I don't want to wait, if we must wait until the cheesecake has cooled to 70 before we can eat it, how long must we wait? I don't like waiting. What's that from? It's a funny movie. I don't like to wait. Okay, so here's the thing. Okay, it starts off by saying the temperature rate of change is directly proportional to the current temperature minus the surrounding temperature. But here's the thing. We're going to switcheroo it. Let y equal T minus some constant Ts, surrounding temperature. In this case, it's 35. Note, and I'm just going over what the book shows, dy dt, when you derive with respect to little t, time, is dt dt. What I did that for, what he does it for, is you can replace this and say, oh, this is the same as saying dy dt is equal to ky. Oh, so that allows us to say, therefore, y itself is some sort of constant, whatever it is, e to the kt. Okay? That's what it allows us to say as a function of time. Wonderful. Here's how you unravel this problem now. You go, okay, I know there's a time, I know there's a temperature, but then you have this y fellow also happening. So let's take the problem and break it down the way we did the others. Okay, it's a cheesecake's taken out of the oven and placed into a fridge. What's its initial temperature? 165. It's right there. Okay. Whoa, what's the surrounding temperature? 35. Now we have to think these things through. It's not this as easy as I'm saying, but that's the surrounding temperature. You put it in the fridge. Around it's 35. Then it says, after 10 minutes, it is now 150. Okay, so it is cooling down. And the problem says, I'm hungry. When is it? Question mark. When is it 70 so I can eat it? That's this number. So we're using the 10, the 150, we're using it all. But now this is how you translate it. Instead of going with t, you go with y. So instead of 165, remember y is the temperature minus its surroundings. So we actually have 130. Okay? And for this one, 150 minus 35 gives us 115. And we're interested in when we're at 70. So 70 minus 35 brings us down to 35, doesn't it? Yeah. So see how this is? All we're really asking for is what's that time? So we do the same thing. We're going to accept that we're not going to use the time temperatures anymore, or the temperatures themselves. We're going to use the y column. And that's how you do this. So the initial is, I can immediately write 130 e to the kt. Okay. Making sure I did that right. And then we're going to use we use that guy. Now we're going to use the next data point, which is 10, 115. Apparently, if you plug in 10, y is 115. e to the k times 10 minutes. Now, forgot to do it. Minutes. No, you got to write that in so you don't blow the problem. Okay. So you divide, and you know what? You've seen this before, right? E to the 10k, which means that 10k is natural log 115, excuse me, over 130. And so therefore, k itself is 1/10 of this natural log. And running it through the calculator, what did I get for that one? About a negative 0.0122, a negative 0.0122. Why is it negative? Why is it negative? Because this guy is cooling off. The temperature is decreasing. It's actually decreasing. Negative. Get a negative there, right? Okay, and the last part then is, what's the time when y is 35? So you plug in 35, and over here you've got the same formula, e to the kt, but you know what k is now. So now this time you're solving for t itself. So let's do that. We've got 35 over 130 is equal to e to the kt. So therefore, kt is natural log 35 over 130. So therefore, t is equal to natural log of 35 over 1. Oops, let me do that better. I'm so excited to know the answer. I'm hungry. 35 over 130 divide by k. Now remember, put that in, store it. You want to store that in your calculator and use it in this equation right here. And if you do it and you do it right, what I got is 107, I think. You get 107 minutes. That's why up here it's important to know it's minutes, which is the same thing if you want to do this as 1 hour, 47 minutes. And if you go in there a second sooner, someone's going to smack your wrist and say, stop. So that's that one. Now I'm going to cruise. You can pause. I'm going to cruise up here and say, here you go. You try this one. Pause it. Okay. And start it again. And here's what I would do with this one. So here we got mystery fluid, 40 degrees, 70 degree room, 1 hour later. Okay, so we're ready to go with this thing. It's going to be this. I'm going to actually go right to it. Y is equal to some m e to the kt. Here's your table. T, temperature, and y, which is temperature minus the surrounding temperature. This is kind of unfair. The one I gave you is different from mine, but you know, maybe it freaked you out with the negatives, but this is what we've got. It's 40 degrees at the start. The temperature of the surrounding is 70 degree room. So y is 40 minus 70. Yeah, I did it this way. I got a minus 30. It said 1 hour later, it's risen to 45 degrees. So 45 minus 70. What did I get for that one? Minus 25. So the question is, how long will it take for it to rise to 60 degrees? So put a 60 here, and the question is, how long does that take? Okay, well, you still have to go 60 minus 70 is minus 10. So we're going to cross out the t and use the y, and it's the same problem. So the first thing you got is y is the initial, believe it or not, negative 30 e to the kt, and it works. That's your first part. Now we're going to find k. 1 hour later, you're at negative 25 times 1, right? So e to the k is equal to, well, it's 25 over 30, watching the negatives cancel. So k itself is the natural log of 25 divided by 30. And what do we get there? For that one, I got negative 0.182, I think. Negative 0.182, roughly. But I don't know why. Now I am flummoxed. What happened there? Did I write down the wrong number? I don't know. I got that number. Okay. It worked. But I was about to say, hey, look at that. It's a negative, and therefore it's decreasing. Is y decreasing? Let's look. No, they're both increasing. So I'll put a question mark there to myself. What the heck happened there? unless I have it wrong. But it worked out because what happened next was the following. I go, well, when y is negative 10, right, solve for t this time. Oh, what is t? Well, you go, it looks like e to the kt is equal to 1/3. So k times t is ln 1/3. So t itself is ln of 1/3 over k. And in that case, they worked out, and I got roughly 6.02. And I would say, what was it again? I did it every time. Hours. So you're going to have to tell people in order to, so basically this mystery fluid rises to 60 degrees in 6 hours. If I did that right. If I didn't, I'll be embarrassed because this is going to go on YouTube. But that makes sense. When I did, it used to say water and it was 6.02 hours. Now that's not quite right. So unless I'm missing something here, I might have gone too fast. But I think that you see the process. So last thing I want to say is a hint about problem 16, which is actually a show your work problem. So it says there's a murder investigation. The temperature of the corpse, I love this problem, by the way. I feel like a coroner. The temperature of the corpse was 32.5 degrees at 1:30 p.m., 30.3 degrees an hour later. Normal body temperature is 37 degrees, and the temperature of the surroundings is 20 degrees Fahrenheit, or Celsius. So when did the murder take place? All I can do is hint. I want you to goof with it. You're going to go T, you're going to go capital T, you're going to go Y equals T minus the surroundings. You do the same thing. The only thing that's different is you're going to have to go back in time. So the time you're going to get is negative. Okay, you're going to get T. Okay, so if you put this stuff in, here's what I would say. Start off with when you found the corpse, which was at 1:30. Okay. So this is really 0 means 1:30 p.m. in the afternoon, right? That's what it says. Okay. And the temperature of that corpse was 32.5 degrees, so 32.5. Hey man, the surrounding temperature it said was 20. So y is 32.5 minus 20, or 12.5. You get the gist, right? So you're going to have to find, that's what I would do. And then, of course, you're going to get a negative, which really means go back in time. And that's it for this one. Have fun studying.